Hey guys, welcome back to another dynamics video. So in this video, this is in preparation for your final. We're going to be talking about moments on rotating bodies. In this case, it's going to be this pulley here. So for this problem, it states that there's a black rod fixed, right, and it's connected to this blue pulley with no friction. There's a red rope that loops over this pulley and does not slip. And then the pulley has a mass of 2 kilograms, a radius of 1 meter or 0.1 meters, and a radius of gyration of 0.1 meters as well. The mass of block B is 1 kilogram, and the mass of block A is 2 kilograms. And it doesn't say it, but the problem wants us to find the speed of A, right, after it falls 2 meters. Okay. So there's going to be a couple steps to do this. So for this first one, or whenever you see like a radius of gyration or something like that, that's essentially a sign that you're going to need a moment of inertia. We don't have to start there. We can start just by analyzing it. So let's see. So we want to find the speed of A, right, after it falls. So this block A, is going to be accelerating at some acceleration not given. And we're actually going to need to know that to figure out the speed eventually, right? So we need to find an acceleration, but we're not given any acceleration. That's a giveaway. We're going to start using free body diagrams. So let's do that. So let's create some free body diagrams of A and some free body diagrams of B, or whatever else we need, right? So I'm going to say right here, I'm going to put my free body diagram of A. Right? And we'll just label it as this red block. Right? So A only has two forces on it, right? It's got a tension from this cord, so we'll just call that TA. And it's got a contact, force at a distance, right? So it's got this mass of A times gravity. Okay, so can we sum forces here? Yes, we can. So we get, when we sum forces, so we'll just sum them in the y direction. That's the only direction we have. We'll assume, let's say upwards is positive. That TA minus MAG equals, and then the mass of A times the acceleration of A, right? So this variable is what we're looking for, right? So we have this one equation with two variables, so we can't solve it just yet. Let's see what we can do with another free body diagram. So let me lock this thing in place and then scoot this equation down. So let's move it down here just to keep it organized. And then I'm going to do the free body diagram of B over here next to it. Right? So let's try B next. So free body diagram of B. So what do we get when we do this? It's a very similar one, right? So we have this block. And then we have the tension up here pulling up, so tension of B. And then going down, we have, not erase, we have the mass of B times gravity. So these things are on the same cord. Why did I label them as two different tensions, TA and TB? Reason is because this thing, or this pulley, has a, what's it called, inertia, and because these things are accelerating, right? If they're accelerating, then we can't say that the tension in this, right, in A, is the same as the tension in B. If we want to break it down, we have to do free body diagrams and show the acceleration. Okay, basically, we can't say the tension of A and tension of B are the same, right, because these two blocks are accelerating on a pulley that has mass, right? So these are going to be different tensions. So now if we sum forces for here in the y, so let's sum forces in the y for B, we're going to get that TB minus MBG equals, and then mass of B times the acceleration of the B block, right? So this acceleration of the B block is also going to be A, and since these are connected by a cord and tension, right, they're going to have the same acceleration. Only thing is, one of them is going to be translating downward, probably block A, and the other one is going to be translating upwards, right? It could be flipped, maybe B is going down and A is going up, but they're going to be going in opposite directions, right, based on the rope equation, with the same magnitude, right? So for just to keep our assumption simple, let's assume up is positive again. So A is actually going to have a negative acceleration of A. So let's put a negative here. And then B is going to have a positive, right? So we can leave this, put that positive or leave it there. Right? So they're going to be moving with that second magnitude, but since this is a vector, A is going to be moving in the negative direction, and we count up as positive. Or we can assume it is. Okay, so what's next? So we have these two equations. We have the tension of A, tension of B, unknown. We have this acceleration, right? These two are the same value, unknown. And then everything else is known, right? We know the masses and we know gravity. So we have 3 variables and 3 equations. Oh, sorry. We have 3 variables and 2 equations, right? So we still need a third equation. Well, we haven't done our moment equation, right? Because this is a bunch of moments, this whole thing. So what we can do is we can sum the moments about this center of mass of this pulley, right? So what forces do we have on this center of mass? So we have a tension here from B, so this is that same tension. And then we have this tension here from A, right? TA, right? And these are both, what did it say the distance was? 0.1 meters apart. Okay, so let's write our equation. So let's say we wanted to sum moments. Let me make this nicer. Sum moments. How can I make this organized? I'm going to move all this stuff out of the way. Sure, up there for now. It's going to block a little bit, but that's fine. So, remember this was positive. Okay. So, let's sum the moments about that center of mass of the pulley. So, about the pulley. Right. And let's just assume, like we always do, that counterclockwise is positive. Right. So, you can make any assumption here. So if counterclockwise is positive, then how is TA pulling it? TA is going to be pulling the pulley this way, which is clockwise, so it's going to be a negative TA, right? So we're going to have negative TA, and then a moment is always a force times the distance, right? So what is this perpendicular distance from the center of mass? That's going to be the 0.1 meters. So negative TA times 0.1, and then that's our first moment. And then our other moment is going to be TB. So TB is also 0.1 meters, but this thing is going to be rotating it in the counterclockwise direction or the positive direction. This is going to be plus TB times 0.1. Right? And those are only moments, and that's going to be equal to the moment of inertia times the angular acceleration. Right? So it looks like we have more variables that we don't know, right? But we do know the what's called moment of inertia. We calculate that, and we know that the moment of inertia just equals the mass times the radius of gyration squared, right? And we were given both of those values. So the pulley mass was given as 2 kg, so 2, and then our centroidal radius of gyration is 0.1, and then that value squared. When you do this in a calculator, it's 0.02, I believe. So that's our moment of inertia. So we can actually plug that value in there. So 0.02 times our angular acceleration. Now it still looks like we need to deal with this angular acceleration, right? Because like, what is that? That's another variable that we haven't accounted for, right? And we can do it. We can make a special point equation, or a very easy way to simplify it, and it'll save you time in your exam, is to realize that in this situation you can also use the shortcut. I'm going to erase these forces for a sec just so we can do it. So I'm going to put it over here on the pulley. So we know what the shortcut, right? The velocity at any point equals the angular velocity times the distance, right? As long as one of the points is a fixed point, right? And they don't have any relative terms, right? So these 2 points where this A connects, well, this rod connects, not this rod, this rope connects to this pulley, and this center point are a fixed point and a point, what's called, with no relative velocity, right? But we can also say, and then we can actually do the derivation, but I hope you can just believe me, is that the acceleration for a point with similar circumstances is equal to the angular acceleration times the distance still, right? So what does that mean, right? This thing is going to have an angular velocity. Let's just assume, because we assume that A is going down, it's going to have an angular velocity clockwise, right? So angular velocity is going to be in that direction, right? Then what does that mean? That means that the acceleration vector is going to be in this direction. That pink looks too close to red. I'm going to put it in green. The acceleration term, right, is going to be going down, right, because this thing's moving. And then this distance is this still the 0.1, right? So what does this equation tell us? Remember, we had that the acceleration equals the angular velocity times the distance. We can rearrange this and get that the angular velocity equals the acceleration times the distance, or divided by the distance, right? And then our angular velocity equals, let's start plugging in the terms we know. So on the bottom, it's going to be that 0.1 distance. And on the top, it's going to be A, right? But since we're saying A is going downwards in this equation still, and we decided downwards is our negative term or our negative direction, it's going to be negative A, right? Just to keep the, what's called the vectors in order, right? So we can actually plug this value over here, All right, so let's go ahead and plug that in. So when we do that, let's see, this is now negative a over 0.1. Okay. And now let's count our variables in our equations, right? So we have TA, right? All these TAs. We have TB, all these TBs. And then we also have A, right? All of these A's. Right, so we have 3 variables and 3 equations we can solve, right, for all of them. So I'm going to put them into a solver. I'm not going to solve this one by hand, but you can choose what to do in your exam. When I do that, I got these values. I'm going to leave it there for a sec so you can look at it. Right. And I'm going to write it down over here. So this is what I got on my Mathematica. This is how I would solve it. And I got that A equals negative 1.962. This is assuming that up is the positive direction. If you assume down is the positive direction, then you get a positive value here, of course. Right, so that's my acceleration. Okay, from there, problem's still not over. We still want the speed of A after it falls 2 meters, right? So for that, we're going to bust out our kinematic equations. Right? So we know that x equals x naught, right? In this case, we can replace it with y. Let's just do that. Y equals y naught. And then, what was the equation? I forget. Okay, I'll put up the equation. That's why we have a cover page, right? So we can use these equations. This is a kinematic equation with velocity and acceleration and position, which is all the things we want to know and have. So let's start plugging stuff in. So we want our velocity term, right, after it falls 2 meters. So this is going to be the term on the left, so v squared still, equals v naught. Since this thing, I'm assuming, started from rest. It doesn't say explicitly, but we can assume it does because we weren't given an initial velocity. Yeah, we'll just assume it starts from rest. 0 here, so 0 squared. Plus, and then our acceleration, right? So we have our acceleration in the y was negative 1.962. And then times our x minus our x naught. So we want to know that when this thing travels down 2 meters from the initial position. So let's say the initial position was 0, right? So that's x naught. And then we want this thing to travel downwards 2 meters, right? So we said that downwards is negative. So this is going to be when it reaches that -2 position. Right? There's a lot of negative signs in these equations I'm writing. You can fix that by counting down as the positive direction. That saves it a little bit, just a couple less, but it's up to you. So let's solve this equation. So we get that v squared equals, and then I'm going to pump all this into a calculator. Calculator. So 2 times negative 1.962 times -2. Okay. 7.848. Right. So we'll get that here. V, when we do the square root, is equal to, let me square root this number, 2.8. Right, so this is the velocity, so this is negative 2.8. The question asked for speed, so you could probably just do positive 2.8 since that's a scalar term. But yeah, so this thing is moving after it falls 2 meters, 2.8 meters per second downwards. I hope that helped. So for these type of problems, if it's asking for, let's walk through our steps. If it's asking for something where you need an acceleration and you're not given an acceleration, you're definitely gonna need a free body diagram for your exam. You guys are definitely gonna need some free body diagrams. Just make sure that if you see something spinning with a moment of inertia or something like that, if it's given, that you can write these moment of inertia equations. So write these moment equations. And make sure you always keep your sign conventions in the correct direction, because flipping a sign will mess up your answer completely. Yeah, I hope this video helped. You guys are free to reach out if you have any questions. That's going to be it. See you.